So can you guys see my screen?
Yes, sir.
Okay, good. Yeah, so for people who are joining for the first time, I would just introduce myself. So I'm Rajat Masiwal. I'm a graduate student at IISc. I work on atmospheric science, basically the fluid flow in the atmosphere. And so I've been taking these sessions. I guess the phase one I took for 12 weeks where we covered the engineering mathematics portion. Not all of it, but I suppose most of the topics we covered. And then on the last week of our phase one session, we had started fluid mechanics. And I guess then after that, we had to stop for a while and we have rejoined again. And so we'll continue with our fluid mechanics. And so here in this slide, I've copied the syllabus from the GATE website for the fluid mechanics. And if you look at the past 10 years or so, you will see that almost around 7 to 9 marks of questions uh, they will ask you from this subject. So again, this becomes a very critical topic for you to study. So if and I think when we were doing mathematics, I had told you that it was around 13 or 14 marks. So roughly you can expect 20 to 22 marks of purely fluid mechanics and mathematics. And if you are good at mathematics, I would say half of the fluid mechanics questions you can do just by that. So it's very important to focus on these two topics. And knowing this, we will start today's session by looking at one problem from fluid kinematics. So this is a very similar problem to what we had done in the last week, not the last week, but the last session. And most of you who had attended the last session can solve it. But for those who have joined for the first time, I would just solve this one and tell you guys how it can be solved. So this is from GATE 2017, set 1. And the question is, for a steady flow, the velocity field is, and they have given some two-dimensional velocity field varying in the I direction and the J direction. And they are asking us to calculate the magnitude of the acceleration at 1 comma minus 1. So those who had attended last session, can anyone tell me how this can be done? It's pretty straightforward.
Material derivative of V.
Right, yeah, exactly. So let's see what the material derivative of V is. So here I have written it down in the component form. For a 2D flow, so this flow is two-dimensional, meaning you will have the velocity field V being some u I cap plus v j cap. So you have the u component in the x direction and v component in the y direction. And then you can write down the total acceleration, which comprises of the local acceleration. So these two are your local acceleration terms. And then this term, which comes from the advection of the flow, is called as either the convective or the advective acceleration. So, I guess this is like your conventional acceleration, which you also get for any solid body. But since we are studying fluid here, which shears and is not solid but a continuum, you will get this advective acceleration, which just gives you the sense of the flow, the fluid being advected by the flow, which gives a additional acceleration to the flow. So if you know these two formula, so okay, yeah, this is also called as the material derivative. The So this capital du dt and capital dv dt is called as the material derivative. And your acceleration in x direction will be given by the material derivative of u, whereas acceleration in the y direction will be given by the material derivative of v. That's all you need to know. And once you know that, then I guess it's just a matter of doing your partial differentials, right? And you'll get to the solution of this. So let's see this. First is, let's note down what is the velocity field. So this is minus x square plus 3y I cap plus 2xy j cap. So we can see that you have the u component of the velocity field as minus x cube plus 3y, whereas the v component of this velocity field is 2xy. Now let's try to calculate the partial differential of u with respect to x. This will just be 3x square, whereas the partial differential of u with respect to y will be 3. Similarly for v, we can see that the partial differential of v with respect to x will be 2y, and with respect to y it will be 2x. Now if we have all this information, we just need to plug the formula. So we have just seen that ax, which is nothing but the material derivative of u velocity, and if you write it in the component form, you will have a local acceleration plus the advective acceleration. Now in the question they have given that this flow is steady, and this basically means that the local acceleration is 0. There is no change, local change with respect to time. So this first term goes away, and you can simply write ax as u, which is minus x cube plus 3y times partial u partial x, which is minus 3x square, plus v, which is 2xy times partial u partial y, which is just 3. Now since they are asking us to calculate the magnitude of acceleration at 1 comma minus 1, we can substitute for x is equal for x to be 1 and for y to be minus 1, and we can say that the acceleration x at 1 comma minus 1 will just be minus 1 minus 3 times minus 3 times 1 square, which is again 1, right? Yeah. And then plus 2 times 1 times minus 1.
Excuse me, sir.
Yeah.
So I can find that it is the minus x square plus 3y u.
Mm, okay, yeah. Yeah, thanks for spotting this. Okay, yeah. So we made a small mistake here. This is not x cube, this is x square. So then I guess this also becomes 2x, just simply 2x. And yeah, here also we have to make this similar change. So this will be x square and this will be 2x. Yeah, thanks for correcting this, Ashwin. So yeah, this will be 2 then, and I think this one is correct, the second term. So if you solve this, you will get that ax at 1 comma minus 1 will be, so this is minus 4 times minus 2, which is plus 8, minus 2 times 3, which is 6, so this will be 2 meter per second square. Okay, maybe we don't need to write the units because they have not explicitly told us which units these are, but yeah, you get the point. Similarly, for AY, you can write the formula again. Now I will not write the local term because the flow is steady, and we can just say that this would be u partial v partial x plus v partial y. Now again substituting, so this will be minus x square plus 3y times dv dx, which is 2y plus 2xy times 2x. And we can now substitute our 1 comma minus 1 point here, and we can see that this will be minus 1 minus 3 times 2 minus 2 plus, so this will be 2 times 1 times minus 1 times 2. So if you solve this, ay at 1 comma minus 1, you'll get 8 minus 4, which is just 4. So the total acceleration in vector form for you will be 2i cap plus 4j cap. And since they are asking us to calculate the magnitude, basically you have to just calculate the magnitude of this vector, which will be nothing but 2 square plus 4 square, and this is under root 20, which can also be written as 4 times 5, and then you can, I guess, take the 4 out, which will be 2 out of the square root, and 5 root 5 will remain. Yeah, so option C will be the correct option for you. So I guess even in the last class we had seen lot of these questions which are coming recently in the GATE exam. So it's just a matter of doing your calculations correct. Just for an example, you saw that how I wrote, just by mistake, I wrote x cube instead of x square. And if you proceed with that, you will eventually end up with a wrong answer. So please make sure you write whatever is given in the question very carefully at the start of your at the start when you're solving, so that you don't end up doing the whole solution and later finding that okay, either no option is matching or you're getting an incorrect answer. But anyway, if anyone has a doubt in this, they can please unmute themselves and ask.
Sir,
Yeah, can you be a little louder? I can't hear you. I think someone is unmuted.
clear, sir.
Yeah, please go.
Sir, phase 1 classes available in YouTube, sir.
Uh, okay, let's talk about the recordings maybe at the end of the class.
Yes, sir.
Okay, yeah. So anyone else has any doubts?
No, sir.
Okay, okay. So if not, let's move on to the next question.
Yes, sir, please.
Yeah. Okay, so now we'll switch gears and we will see a different topic, and we'll see it through this simple problem from GATE 2020. And this problem is of, well, Bernoulli's equation, we will find out, but let's read this problem. Consider a flow through a nozzle as shown in the figure below. So you have some kind of a nozzle flow here. And the air flow is steady, incompressible, and inviscid. They've given us all the properties of this flow. And the density is also given to us. And we are supposed to calculate the pressure difference, P1 minus P atmosphere. So here at point 2, you have atmospheric pressure. And at point A, you have some pressure P1. And we are supposed to calculate the difference between these two pressures. So let's look at the theory we need to solve this. We simply need to know the Bernoulli's equation. So one One thing you should always remember when applying the Bernoulli's equation is the assumptions. So you need to keep these three assumptions in mind. Yeah. When the flow is steady, and this basically means your partial u vector partial t is equal to 0. So there is no local acceleration. And when it is inviscid, which means the viscosity is 0. So this is like an ideal fluid where you have no frictional effects coming from frictional or the viscous effects. And when the fluid has a constant density, so this means basically rho is constant, then there is this there is this three terms, or you can call it the energy, which is conserved. And here the first term represents the pressure head. So this is P upon rho g, where P is your pressure, rho is the density, and g is the acceleration due to gravity. And it is usually called as the pressure head. V square by 2g is nothing but the kinetic energy head, Ke head. And this z is the potential head. So the sum of these three terms are conserved when we talk about Bernoulli flow, and that's all you need to know in order to solve this question. So let's look at the solution quickly. So again, let's write down what is given to us. So at P1 the pressure is P1, and at P2 the pressure is the atmospheric pressure. At P1 the velocity is V1, and for P2 the velocity is given, this is 50 meter per second. The area at A1 is given, which is 0.2 meter square, whereas at A1, and at A2 it is 0.02 meter square, or you can write it as 2 into 10 to the power minus 2 meters square. Now in order to apply the Bernoulli's equation, we first need to find the velocity at point 1, which is for the time being not known to us. But simply by looking at this flow, we can just say that, okay, this is a one-dimensional flow, and you can use the 1D continuity equation, 1D mass continuity equation you can use to deduce the velocity at point 1. So the 1D mass continuity equation simply says that A1 times V1, so that is the flow rate at this junction 1, will be equal to A2 times V2. So this has to satisfy because the mass has to be conserved. So whatever is coming in here has to come out of here. So everything else is known to us. Simply we can say that V1 is nothing but A2 by A1 times
So that 5.
V2. Avijit, yeah, you had some doubt?
Yes, sir. This one will be the 5 meter per second. The value of
V1,
V1.
is it?
Yeah.
Yeah, I think you're right. So A2 will be 2 into 10 is to the power minus 2. A1 is 2 into 10 is to the power minus 1. And V2 is given to us as 50. So yeah, so this comes out to be 5 meter per second, as Avijit correctly pointed out. So now, since we know V1, we are in the position of calculating this P1 minus P8 here. How? Let's apply our Bernoulli's principle, which says that P over rho g plus V square over 2g plus z is a conserved quantity. So we can take these two junctions and say that P1 over rho G1, okay, G1 and G, G. So P1 over rho G plus V1 square over 2G plus Z1 is equal to P2 over rho G plus V2 square over 2G plus Z2. And now we can see that both of these junction, if we just apply this along the streamline, are at the same Z location from, let's say, some reference datum. So this is, let's say, 0. From this reference datum, P2 junction and P1 junction along the streamline have the same Z. So this does not change really. And it's just that we need to calculate P1 minus P8M. So we can take, okay, we can first substitute the values. So this will be P1.
1522.125.
1.5.
1522.125 आ रहा है.
But
नहीं यार
yeah, I think
1.5.
so. There's this trick here. I think Abhijit, you missed this trick, and if you miss this trick, then you lose out on 2 marks actually. So you have to check what they are asking your answer in. The units are very important.
Okay. Now I got it.
Yeah. So anyone can, I guess, apply this Bernoulli's formula, and anyone can do this mass continuity. They are just trying to trick you by slightly at the end putting this kilopascal instead of pascal. So yeah, you have to take care of that. But okay, for people who are still not able to solve it, let me go through this calculation once. This is P1, and let's keep writing it as rho g for the time being. And V1 we have just calculated is 5, so this will be 5 to the square over 2 times G, and P2 is P8M rho times G plus V2 is 50, so this will be 50 to the square times 2G. So from the denominator we can cancel out G everywhere and just say that P1 minus P8M, and there will be a rho at bottom, is equal to 50 square minus 5 square over 2. And I guess this is a straightforward calculation. P1 minus P8M is rho, which is 1.23 times. So this will be, I guess, 2500 minus 25. And yeah, you guys can do this calculation probably. So yeah, so I think Avijit had said this, right? So okay, this will be in the end 1522.125, but this is pascals. Now
Yes,
in the
sir.
question they are asking us to write down the pressure difference P1 minus P atmospheric in kilopascals. So you simply just divide by 1000, and then I guess this that much pascal will just be 1.52 times 10 to the 3 pascal, or 1.52 kilopascal. So that is the correct answer to this problem. So Avijit, now you get it right.
Yes, sir. Yes.
Yeah. So please also look at these units at the end. If they
Yeah.
make the question very simple, you have to read the question again, because then they will use some kind of trick in order to make sure that some of you get it wrong. Anyway, anyone has any doubts on this? Okay, I think this is clear to everyone. So if this is clear, I guess we have a very similar question here, and I would like you guys to solve it and put your answers in the chat, and we will see if people really understood the last question. Okay, maybe before you start solving this, there is one concept you need to know. So let me read the question. So this is from GATE 2020, set 2. Water, some density is given, 1000, just to make your life easier. Flows through an inclined pipe of uniform diameter. The velocity, pressure, and elevation at section A are VA, 3.2 meter per second, PA, 186 kilopascal, and CA, 24.5 meters. So this is all the information at junction or section A. And similarly, sorry, similarly, they have given you the information at section B. Now, okay, this acceleration due to gravity is also given, 10 meter per second square. Now they are asking us to calculate the head loss due to friction. Now in the last problem, we simply applied the Bernoulli's principle, assuming the flow was frictionless. But if there is friction, you can just simply modify this Bernoulli's equation to get the estimate of your head loss due to friction. So here before we did not have this term when there was frictionless flow, but when there is some friction, we say that maybe this friction uh, eats up some of your energy from going from junction 1 to junction 2, and that if you add that lost energy on the right hand side, you again recover this conserved quantity. So this is your head loss, let's say due to friction.
Your velocity head would be 0.
uh, yeah,
सर
it is, yeah.
इसका 8 मीटर है क्या?
Uh, yeah, I don't remember the answer. Let all other people also solve it, and we will see what the correct answer is. So I guess there are a lot of people here, so I would ask everyone to please take your pen and papers out and start solving this, and put your answers in the chat. I'll probably give you guys maybe 5 minutes. 5 minutes is more than enough for this, but okay. If you are not ready, get prepared and please start solving it. Okay, we started getting some answers already. A lot of people are saying 8 meters. I suppose that might be right. Yeah, more or less everyone is agreeing on 8 meter. I think Satyaban 8 meter is correct.
Okay.
Yeah. So Anyone who did not get how to solve this, they can just raise their hand or unmute and ask. If everyone got it, then I guess there is no point solving it again.
Hello, sir.
Uh, yeah, yeah.
I confused in the density how to calculate that is sir.
Oh, okay. Okay, fine. Let's.
Okay, sir.
Yeah, yeah. Let's. So you are confused in density. You are saying.
Yes, sir.
So if you look at the formula, density appears in the denominator of the first term in the pressure head, and one of the assumption for applying Bernoulli's equation we just saw was a constant density fluid, right? So density does not really change, and here they have given you the density to be 1000 kg per meter cube. So it really won't change. You just need to keep account of this density on the left and the right hand side. That's all. So if you have this PA, that is 186 kilopascal.
Okay, sir.
Yeah, you got it right.
Okay, sir.
Yeah, okay. So I will skip the solution, or anyone else who wants me to solve this? I don't think so. I think, yeah, everyone could solve this. So yeah, I'll skip solving this. But okay, you guys can, if you have not finished doing it, you can try it later. And the answer should be 8 meters. You simply need to apply this formula. And I think, as Avijit said, the velocity head will cancel out because you have same velocities at both the sections. So VA and VB are same. So V square by 2G will be same left and the right hand side. And then it just becomes a matter of calculating the pressure difference in the pressure head and the potential head. Okay. So let's see a little different question now. This one is from GATE 2022 set 2, and this requires knowledge of the buoyancy force. We will see what that is, but let's first read the question. So a uniform wooden rod, and they have given us some properties of this rod, properties like the specific gravity, diameter, and the length, so the dimensions, is immersed in the water and is hinged without friction at point A. So it has been hinged here, and it is assumed that it's a frictionless hinge. A solid spherical ball made of lead, they have some ball here, is attached to the free end of the rod to keep the assembly in static equilibrium inside the water. So the whole of this assembly is in static equilibrium. Now for simplicity, assume that the radius of the ball is much smaller than the length of the rod, and assume the density of the water to be 10 raised to the power 3 kg per meter cube. And in the end, you have to find the radius of the ball. Okay, so let's see what we need in order to solve this question. So you need to know about the buoyancy force, and this is just the force exerted by the fluid on the body immersed in the fluid. So let's say you have some container which is filled with fluid, and you drop a big ball inside this. So the radius of this ball is r, and you drop this big ball inside the in this container. So intuitively, what the water will do, the water will try to push it upwards, right? So this pushing of the ball or the force exerted by the fluid on the ball is what is called as the buoyancy force. And the formula for this force is simply this. And here, so this rho f is the density of the fluid, g is the acceleration due to gravity, and vfd is nothing but the volume of the fluid that is displaced by this ball. So that will just be equivalent to the volume of the ball itself. And then if you calculate this, you will find that this is the amount of force that the fluid applies on the ball. So this is called as the buoyant force. You might have seen, let's say you have a bucket and you place some body inside this bucket filled with the fluid. You will see that this body or any object tries to come up. So that is because of the buoyancy of that fluid. And also you need to know what specific gravity is. This is straightforward. Specific gravity is just the ratio of your body divided by the ratio of the fluid. So it's just the ratio of two densities. So once you know that, you can solve this problem. Yeah, and let's first try to see what is given to us. So I will call this wooden rod as R. So the specific gravity of this wooden rod is 0.6, and the density of water is given as 10 to the 3. So this can just be 0.6 times density of water if rho W is the density of water, and its diameter. So diameter of the rod is 4 centimeters. So in meters, this will just be 4 into 10 is to the power minus 2 meters. And the length of the rod is 8 meters. Now for this ball, so if we write down for the ball, density of the ball is, since the specific gravity is 11.4, so the density will be 11.4 times the density of water. And the radius of the ball is unknown. That is what we need to find. So if we draw the free
59, sir.
what?
3.59 cm.
Yeah, I think this is correct.
Sir.
Yeah. So Satyaman, what did you do to solve this?
सर मतलब कि buoyancy force will act as the rod के center of mass पे act करेगा ऊपर,
Right, yeah.
और weight नीचे की तरफ है, तो resultant ऊपर की तरफ है.
Yeah,
Plus rho into Vg,
into Vg, yeah.
which is 4 meter मतलब along the rod from point A, and for the ball from point A to the 8 meter उधर से नीचे है, तो नीचे की तरफ force लग रहा है, तो moment about A is 0 finally.
Right, yeah. So, okay, the point is that movement about A should be equal to 0 since the body is in static equilibrium. Yeah. So the whole assembly is in static equilibrium inside the water. So it's a good idea to let's just draw the free body diagram. So you have this point A here. Let's say this is your rod and this is your ball. So there are bunch of forces that will be acting in the whole assembly. But since the whole assembly is in static equilibrium, we have to remember that at this hinge point, the moment will be equal to 0. So let's first see how many forces there are. So for the spherical ball, you will have this weight of the ball. So let's call it W of ball acting downwards, whereas since it is immersed in a fluid, you will have some buoyancy force which will act upwards. So let's call this FB, FB being the buoyancy force on the ball. Now we can consider this rod as a point mass somewhere in the middle. So at the centroid of this rod, you will have this weight of the rod acting downwards again. So this will be W times R. Whereas there will be a buoyant force which the rod will also experience. Let's call this Fr. So these are the four forces that will be acting on this whole assembly. And okay, maybe we can. So if the length of the rod is 8 meters, so this distance will be 4 because this will be the centroid, and this distance will be 4. So from arguments of similarity, we can say if this is x, this will be at this point 2x. Why do we need these distances? We will see in a moment. Since this is in static equilibrium, the sum of all the moments at this hinge point A will be equal to 0. So we can just say that Fr minus Wr, since they are in opposite direction, times x will be equal to F, or you can just say maybe Wb minus Fb times 2x. So if you sum these moments up, you will get this kind of an equation. Now all you need to know is what this Fr, Wr, Fb, Wb actually are. So we have to calculate this, and this x becomes arbitrary now, and you can cancel out x. So let's try to see. So calculating weights are always easy. So let's calculate the weight of the rod. This will just simply be the density of the rod times the volume of the rod times g. So this is just volume times density times gravity, or so mg. So this gives you the mass of the rod, and this is g, gravity. And density of the rod has been given to us as 0.6 times density of water. Volume of the rod, since this is a cylindrical rod, volume will be pi times, and this is r square times L, length of the rod, and g. Similarly, we can also calculate the weight of the ball. That will be the density of the ball times the volume of the ball times g. Now the density for the ball is given as 11.4 times the density of water from here. Volume of the ball is, since the ball is spherical and the volume of a sphere is given by pi by 3, 4 pi by 3 r cube, and this r is unknown to us. Actually, that's the uh, thing that we need to find, times g. Now these two are slightly different. So here let's see what kind of buoyancy force acts on the rod. So since that will be applied on the rod by the fluid, so we will have density of the fluid. Okay, maybe I should write. Yeah, density of the fluid, which is the density of water, times the volume displaced by this rod, which will be equivalent to the volume of the rod itself. So volume of the rod times g. whereas for the ball it will be again density of the water, volume of the ball, because at this location the volume of the fluid displaced is by the spherical ball, and again times g. So again you can just write rho w times, similarly the volume of the rod which we had just seen is pi r square lg, r of the rod. Okay, and here it will be rho w 4 by 3 pi radius of the ball cube times g. So now you have all these four terms, and this equation also we have found out by balancing the moments at point A. All that is needed now is just to substitute all these four terms here and then try to find RB, because everything else is known to us.
Excuse me, sir.
Yeah, Ashwin, please.
Sir, actually the thing that they've given us, the radius of the ball is much smaller than the rod, right? So that is for taking the center of mass of ball is at 2x distance.
Exactly. Yeah. Okay. I think I skipped over this point. Yeah. Thanks for reminding me. So they have said that for simplicity, assume the radius of the ball is much smaller than the length of the rod. And if that is the case, then you can say that maybe there is some slight r here, which is much smaller than your some theta times 2x. So you can just neglect this r when you are doing these moment calculations. So that was your point, Ashwin, right?
Yes.
Yeah. Yeah. Okay. Yeah. Thanks for pointing this out. So I won't go through the calculations. If anybody has any doubts on what we did just now, can please ask me. Otherwise, please do this calculation and tell me what the final answer is. And okay, by the way, again here the same thing, just two questions previously we had visited. So you will do all this business and you will find your answer. And if you are like doing everything in SI units, the answer will be in meters. And in the question they are asking us the radius in centimeters. So you have to do the conversion accordingly at the end. So please don't forget that also.
Sir, here since like the hinges, if it is free, then we would just do the net upward force equal to net downward force.
Uh, what did can you repeat? Ashwin? I kind of missed the point in between.
Yes, sir. Actually, here since they've given this rod is hinged at A,
Yeah.
so we are taking this concept of. Otherwise, if it was not hinged, then we would have just done sigma Fy equal to 0.
Oh,
Net
so force
upward force
balance you are
equal
saying?
to, yeah. Yes.
No, but yeah, okay. Maybe if they say that the body is in some kind of equilibrium, yes, then there will be no net force on the body. Then you can proceed with that.
Yes.
So that will be like some hydrostatic pressure which will be acting on the body, balancing the. Oh no, yeah,
Yes.
yeah, no, the weight of the body being balanced by the buoyancy force. Simply that. Yeah.
सर एक बार इसका आंसर कंफर्म कर दीजिएगा.
So, okay, for confirmation, I will ask the others to solve it. If everyone is getting a similar answer, then will say that that's the correct answer. Anyone else has solved it?
3.47 centimeter.
3.47 centimeters.
सर मेरा है 3.587.
Oh, and they are asking us to round off to two decimal places. 3.58, 3.47. Anyone else?
3.58 ऐसा ही कुछ आ रहा है सर.
Okay, someone else also said 3.58.
सर अब अगर आप भी अपने पास आंसर रखेंगे तो वो एक मतलब ज्यादा अच्छा रहेगा सर थोड़ा.
Yeah, yeah. No, I had solved this, but I actually let that's also pretty good. But yeah, that's I guess all I had for today, and we will continue this question next in the next session. And if anyone has any doubts, they can just ask. Yeah, I don't think we will have time. If there is time, I will just go back and do more questions from mathematics and fluid mechanics, because I don't think at the end it would be good if I start a completely new topic. So I am hoping that we will finish fluid mechanics and then we will do bunch of question from. So I don't think we did questions from different gate subjects. So maybe some electrical electronics questions from for this math topic, and questions from engineering sciences also. We only did like 2 3 years, past 2 3 years, because
Yes.
yeah, in the end, what will matter is how many questions you solve and how many different kinds of question you solve. So
So if possible, if we have time, can we do fluid machines or heat transfer? Because it is yet to be covered by other classes as well.
fluid machines, I'm not sure. Heat transfer, I can at least do the radiation part if you guys want at the end, because I actually don't work with turbo machinery, so I'll have to like revisit a lot of theory in order to yeah, in order to like teach you guys, like first learn the concepts again and all of that. But yeah, heat transfer probably we can do, but don't take my word right now because let's see what happens. Yeah.
Sir,
Yeah, Praveen.
sir, this is my first class of fluid mechanics. I want to previous class link, sir.
So okay, yeah. So we had this Google Drive where links from all the previous sessions were there, and yeah, let me see. Can anyone share that if anyone has it readily available, or if not, then I guess I will have to go and check for that. Let me. So in this drive, you will find all the previous sessions recordings as well as PPTs. So for I think 11 odd weeks we had done engineering mathematics. If you want to check that out, you can also check that out. And then the 12th session, the last session of that phase one, we did some introductory fluid mechanics. So if you only want to do the fluid mechanics part, you can just take a look at the last session. Yeah.
Yes, sir. Thank you.
Sir,
Yeah.
sir, if you take the momentum of momentum,
Mm,
how to write the equation? No idea, sir.
can you repeat your question? I think there was some lag.
Sir, momentum of momentum equation, sir. And fluid dynamics topic, sir.
Momentum of momentum equation.
Yes, sir.
What do you mean by that? Momentum of momentum equation.
Sir, Lawn Springer, sir. Lawn Springer.
Yeah,
Hello, sir.
I'm not aware of it actually. I'll have to see. Can you share some references? I'll have to see this.
Sir, okay, sir. I will share the next time, sir.
Sure. Yeah. Yeah.
Okay,
Okay. Yeah. Any other doubts, guys?
Sir, what is the area of research, sir, of yours, sir?